Thanks for coming, everyone. This is a version of a talk that I gave to a much smaller group several months ago. It was pretty well received. It's what I'm working on right now. And so I'm just hopefully explain some of the basic concepts and ideas. We'll go over what RDF is, what language models are, and then why they go well together, which I think is unintuitive to most people, unless you've already been thinking along these lines. Yeah, so we'll go from there. I'm going to start out with a controversial statement. And I'm going to make two controversial statements that are mutually exclusive. So you'll find yourself in agreement with one and in disagreement with the other, most likely. Or maybe you're like me and you feel the tension. So the first one is, language models are pretty neat, and I like them. We never imagined that we'd be able to compute over unstructured text like this. And it really feels like a technical advance. And I like technical advances. I think that technology on net is a real force for good. Especially if you can get the societal structures aligned. So definitely go vote in a few days. But the interest I have in this specific tech is also deeply personal. My academic background is in philosophy and linguistics. So, and then all my work has been in computers and data. So having them merge like this, it's very interesting personally. We have a real serial Chinese room in the room with us right now. That's wild, for those of you who are familiar with philosophy. But the second controversial statement is language models suck, or rather AI sucks, and specifically the way our culture has been using it. It's bad for the environment, it's bad for art, it's bad for labor, or at least artists and labor are upset about many aspects of it. We are drowning in slop and spam and disinformation. And the ecosystem at large has some good people in it, but it also attracts a lot of the absolute worst sorts. And so I have very mixed feelings about working on this stuff. So here's how I've decided to approach it. First of all, just be mindful of the impact. I think we don't, as technologists, have the luxury of doing something just because it's cool or just because we can. You really have to think about how the products we build are going to affect the world. Also, do not talk about this stuff on social media for the most part. Nobody there has a reasoned, well thought out opinion. These are for long, more thoughtful conversations. And the final thing, what this talk is about, is how can we make the tech actually good? If it comes with all these trade-offs, if there's all these negative externalities, how good does it have to be before it becomes net good for the world and a positive force? And it seems like it's here. People are going to be using it, so let's make it as good as it can possibly be. But how? Technology is good. Language models are technology. How do we make language models useful? And my answer is the resource description framework. So hopefully, at the end of this talk, you will sort of see what I see. But first, let's talk a little bit about RDF, what it is, where it came from. So RDF is an attempt to tackle some of the hardest problems of knowledge representation and reasoning. It came about just after the internet, from the same group of people that put together all the internet specifications, the W3C, and a lot of people that came out of the symbolic AI boom of the 80s. So we're trying to reach AI through logic. These people are all giant nerds, and they're really trying to do the right thing and to build like the ultimate data framework. And it's got its pros and cons, but I think to a large degree they succeeded. This is the kind of definitive document, the concepts and abstract syntax, because of course it's abstract. I really love this document. It's quite readable. If you're enough of a nerd, you might find this document sort of inspiring. And I think RDF in general, at its core, is a pretty brilliant technical achievement for clarity and vision around how we can or how we might work with knowledge on computer systems. They're trying to solve this at a very high level. However, RDF today, and many of you may be surprised to see this in a talk at a contemporary tech conference, a lot of people see it the same way they see SOAP or EJBs or Visual Basic or React. It's one of these tech that's it's just not that cool anymore. And of course, it's gone through the whole hype cycle, and now it's very much not in the hype cycle. And there's a few reasons for this that I do want to kind of go over before we get more into the meat of it. One is RDF XML, which is one of the initial formats. I don't know how many of you remember the early 2000s well, but everyone was just doing lines of XML at work all the time. There was a lot going on there. This is a verbose, complex format. It's just honestly not great. But for the early days of RDF, it kind of got really strongly associated with this, even though this is only one of many, many formats you can use. Also, a product of its time is that all the libraries that were written to use it were in the early 2000s. And what are libraries in the early 2000s like? They're all massively over-architected object-oriented programming. This is a historical accident that all the RDF libraries look this way, because it's just that they co-occurred in history. There's nothing about RDF that makes it a good fit for object-oriented programming, and Clojure is actually a way better fit. So I wish there was a good Clojure library for this. Another reason is that there actually are a lot of pretty good, really solid, robust, enterprise-grade RDF implementations out there. And they all cost, call me, money. You cannot just start using these. So there's a real gap in the market for quality, accessible tools. But the existence of all these really heavyweight enterprise tools for RDF does tell us something, which is there's actually a quite established market for this stuff. RDF is being used really productively in science, heavy industry, government, anywhere you need to really model super complex information with precision. So there's a surprising number of domains where RDF-based standards are the standard for modeling data. Another reason is that the semantic web was quite simply overhyped for the time. It's a great idea. We'll link all our data. We can traverse all our data. Everything will be unified, and we will live in this data utopia. But the problem was it required so much manual effort to publish and consume constantly. And all the benefits were like abstract. There was no immediate financial incentive for anyone to actually go implement all their data as linked data and expose it in this way. And so despite tons and tons of books, because it's a great idea, everyone got super excited about it, and then nobody actually did it, and then people just kind of came to the conclusion that this is a bad idea. So this is really what I want. I wish this book got popular, that I lived in that history. But the truth is, RDF is all good parts because it's all separate. All the things that are not good parts are not, they're just kind of the surrounding ecosystem, which we can replace or not choose to use. So hopefully, I can convince you that RDF is great. And what is the elegant core? I'll describe what the actual technology is and how you use it. It's the resource description framework. So let's talk about resources first. What is a resource? A resource is anything in the world that you can talk about. People, fictional entities, abstract concepts, material objects, data, anything that can be the subject of language can be the subject of RDF. How do we represent anything in a computer? Computers can't represent anything, they have bits. Well, literals are easy because they are bits. So anything that is itself can be a resource. Computers do know how to actually have the numbers and strings as resources. We can also represent things kind of abstractly without talking about what they are. These are like variables or pronouns that you can talk about something without ever trying to say exactly what it is. So we can talk about something without using its name, which can be useful sometimes. And then sometimes we do want to name things. And this is a lot of letters to say a unique ID. And really that's all it is it needs to be unique ID. So what are some IRIs, resource identifiers? UIDs, right? They're unique, we know that. Anything that has a known naming authority, so we know the ISBN system, this is guaranteed to be unique. Most commonly, you'll see URLs, and URLs are great for uniqueness because they establish in their domain an authority, and whoever owns that domain takes on responsibility and authority for making sure there's no duplications or ambiguity in the rest of the URL. And these URIs can be resolvable. You can actually hit this in your browser, and it'll ask you what format you want to download Abraham Lincoln's data in. And they can also be non-resolvable. So for example, this is a URI that I made just now, this morning, and it defines my concept of excellence. I haven't written this down anywhere. Nobody knows what it is except for me. But I still can make a URI for it and talk about it. And it's the name of something. You can't resolve this, but I can still use it to talk about that concept in the RDF vocabulary. And of course, because IRIs are pretty long and cumbersome, you can shorten them. Every syntax has shortened prefixes, kind of like Clojure keywords. So when you see a bunch of IRIs around, in practice, it looks a lot cleaner. So why IRIs? Why is unique identifiers so important? Why do we put so much focus into making sure resources are unique? Well, it's because in language, context is everything. Take the sentence, my friend Joe. I just start a sentence that way. What do you need to know in order to make sense of that sentence? You need to know who's speaking. You need to know, do you know Joe or not? That could change the context. Joe who? I haven't said his last name, I just said Joe, right? So natural language is really inherently ambiguous, and we rely a ton on context to fix it. And the problem is we do this with programming too. In most programming systems, when you get data, it comes to you like this. You say, I have a name, and I have a handle, and I have an ID, and now I can process it. But in order for me to process it as a programmer, I need to supply the context. I need to understand the system. I need to understand where the data is coming from. I need to understand what it means, and then maybe I can write code against it. The goal of IRIs in RDF is that they carry their context with them, right? My friend Joe, his handle, well, that's his LinkedIn handle. And when I see that, if you just hand me a scrap of paper that says, oh, well, it's a LinkedIn handle, and oh, that's his social security number, that's the ID. It's not his real one. You know, it carries its own context. The data brings its own values. And this also gets super philosophical really quick, which is probably why I like it. IRIs are very closely related to the philosophical field of semiotics, which is really important for logic, philosophy, linguistics, and literature. Lots of fields use this. There's a ton of thought about how a sign or a symbol can be about something in the real world. That's what this famous painting is about. Like, is it a pipe? Is it a picture of a pipe? Is it me talking about a picture of a pipe? What are the layers of indirection? How do you dereference a pointer in your brain to something in the real world? That's the field of semiotics. And for RDF, it's how do you dereference a identifier in a computer to something in the real world. And of course, you don't actually dereference it, but you can use it in systems with the understanding that it does dereference conceptually something. This is also very similar to the work of Ferdinand de Saussure. He was one of the foundational figures in modern linguistics. He wrote a course in general linguistics in 1916. His concept of meaning was that everything is a semantic network. Every sign or every word gains meaning by its opposition and relation to every other sign in the vocabulary. And that was his definition of meaning. He's like, there's really nothing much more to meaning than that, except it's this network and everything is defined in relation to everything else. So it's like a densely connected graph of all the words, which sounds kind of familiar. Sounds a little bit like linked data maybe, and it also maybe sounds like some other things that we'll talk about later. Okay, so we have resources. How do we have descriptions? Well, we've got resources and IRIs, so how do we express relations between different resources? I think everyone in this room is pretty comfortable with triples: subject, predicate, object, entity, attribute, value. If you're in English, it's subject, verb, object. It is one of the most granular ways of representing a singular piece of information in kind of you can't really decompose it further. You can have a single resource, but then it's just, I say a name. But if I want to say anything about that name, this is about as small as you can get. Yeah, so here's a bunch of things I'm saying about Joe. And they're all different things. I can say his real name. I can say his name according to LinkedIn. I can say he knows me. I can say he's the same as this other IRI. We can just say a bunch of stuff about Joe now. And it's important that both the subject and the predicate and the object of an RDF triple, all three parts of it, are very, very precise. We can be more precise than English. So sorry, the text is a little bit small. But there are two statements here. And one is Luke loves their child. And the other one is Luke loves Clojure. And normally in English, again, semantic ambiguity. But in RDF, I've actually have the IRI of two separate dictionary subheadings of the word love. So I can be very, very precise about what I mean. And if one was not in the dictionary, I could go make up my own IRI that had the nuances that I wanted to attach to that statement. So we're packing a lot of meaning into the IRIs, and we can be much, much more precise than English, and actually much, much more precise than most other data formats. This generality of triples also means that you can go back and forth between almost any other data format. Relational databases, key value, columnar stores, document-based, all of these can be converted to triples. And the operation is actually conceptually similar. Add the context. So an example in a relational database, the context is like, oh, what are all the tables, and what is the structure, and where does the database live? You can kind of compress all that information into the semantics of the IRIs themselves. And then, of course, you can go back in the opposite direction. What does this mean? It means that an RDF data set is a set in the Clojure sense or the mathematical sense. It's just a bunch of triples that are not duplicated because every IRI and every triple is guaranteed to be unique. And we don't need to know anything else about what tables there are or what folders there are or what trees or directory structures or anything. We just have sets. And that means that we can also safely union sets. So this is where the concept of the semantic web comes from. I can take your data, I can take my data, I can just slam them together with a set union, and it's still something meaningful and intelligible, which is not true of most other database systems. It's federation for free. So we've described the core of RDF. That's really it. resources and triples. Nothing conceptually difficult there. But it's worth saying something else about what the designers envisioned. You know, they call it a framework, and with a framework, they want you to build things with a framework, right? And we can describe data, but what more is there? So this guy is actually the primary contributor to the RDF standard, Aristotle. I'm not even joking. He invented the words subject, predicate, and object in the context in which we're using them now. And this entire book is about, you know, the first chapter of this is listing all the types of things that exist in the world, according to Aristotle. And the rest of the book is the foundation of modern Western logic. He builds it all, starting from here. What can you say about what kinds of things? And RDF is really bigger than just data or storing data like we normally think of. It's more than just a spreadsheet or a table or a bucket that I can put data. It's about representing knowledge. And knowledge is not limited to just things I've written down. It's also limited to the things I know because of the things I wrote down, right? It's basically RDF as a system is designed to make it possible to talk about all the things I know, whether I know them concretely or abstractly or in theory, but I never bothered to actually think about them and calculate them. The actual data that is actually sitting on bits in a database is largely incidental to a lot of uses of RDF. So this is all about entailment. Entailment means that given a set of triples, I can derive other triples from them conceptually, either lazily or proactively, doesn't matter. Or if I have a set of triples, I can tell if it is valid according to some definition of validity. And that can be really useful. Because there's so many different ways to do this, the RDF community has a number of what they call different entailment profiles. The best and kind of gold standard for entailment profiles is the entirety of first order logic, which is beyond the scope of this to explain, but those are the symbols on the other sides. The full suite of if, then, else, not, composed with any level of complexity. First order logic is great. It's not great to use as a programmer because it happens to be NP-complete. In fact, it is the NP-complete problem. It is the definitional problem for very, very hard problems to solve efficiently in computer science. So we have a lot of other profiles that do less and are less expressive, but are also calculable over large data sets, you know, before the heat death of the universe. And the most important thing we use these for is to get back some sort of level of a schema and kind of tell what sort of statements are meaningful and what aren't. You know, my date of birth cannot be the color purple. So if I have a data set that says my date of birth is the color purple, I can use entailment over schema to say, no, it's not. I don't accept that data in my database. And same as is important because it really helps with federation. I can say, hey, these two concepts, they start out as separate concepts, but now I'm bringing, after the fact, a third statement, which is these are actually the same concept. And then that means that I can now query across that and reason across that really effectively. And really, there's a large sense in which RDF and all the entailment and logic associated with the RDF ecosystem is the accumulation of 20th century AI, which is all about symbol manipulation, formal logic, rules-based expert systems. You know, you had Psych trying to build a database of every fact in the universe and make, you know, an intelligence would emerge. And people were very optimistic about that, and all these things were getting very funded. And then it turned out that that didn't actually lead to general intelligence. It's very useful in programming systems. Logic is useful, but it doesn't lead to intelligence. So these people all went and built RDF instead. And they brought these concepts specifically in a way that works with the internet era, where everything is networked and everything has the potential to be linked. So that's RDF. 20 years later, little paper out of Google, attention is all you need. This paper defines the transformer architecture, which is the underlying breakthrough that allows all the language models to work. It has an attention mechanism, which basically allows it to train on tokens, like taking their position into consideration, but also independent of their position in a sequence. And once you can train with that kind of flexibility, it just unlocks everything that language models can do today. So natural language processing as a discipline was immediately revolutionized. ChatGPT came out just 5 years later, which is lightning speed. This was like on a tiny little test demo data set. And then they built something giant off of it really, really fast. And I don't need to describe how big a mania it is right now. They're eating the world, at least from a hype point of view, if not from an actual productivity point of view yet. How do they work? I can't tell you. Well, I can tell you, but I cannot tell you in the next 20 minutes. So if you want to do it, go to this URL. This is a really great, Carpathy walks through about 16 hours of dense video where he live codes a mini GPT. I followed through, I did it in Clojure. You can too. You will deeply understand this when you're done. Yeah, I'm not going to talk anymore about the internals of how the model actually works, out of scope. What I do care about is like defining them and like how do we use them and how should we think about them as software developers. So the etymology is actually very straightforward. You take a measure and you have the diminutive form of it, a small measure. A model is a small measure of something. And this is actually really important for what these things are. What is a model? It's a measurement of something. What we're doing is we're taking language and we're measuring it. We're analyzing every aspect of language and we're quantifying it as much as we can, and we're specifying the distances between all the different concepts. We're putting language on a bench and building a small copy and measuring it along every dimension. There turns out to be about hundreds of billions of dimensions, which is why there's hundreds of billions of parameters. So the act of generating from a generative language model is to create replicas based on those measurements. Hey, let's emit some language, but if it fits up with these measurements, that's kind of what the real language is. Or then it looks and acts like language because it's based off of the same measurements we took. And interestingly, an RDF data set is also called a model. Kind of fits more in the second definition here. But it's also a set of measurements about the world, or a set of things I've chosen to say about the world. So what are we modeling? This is a model. What aspects of language are we measuring? What are we capturing? We're capturing grammar and syntax. And we've actually been modeling grammar and syntax since long before we had computers. You could build a simple rule-based generative grammar. We'll talk about that more later, and build a model. But language models absolutely do capture the grammar and the syntax as well. They also capture a lot of the semantics, how the words stand in relation to each other. Remember Saussure. It's almost like we've built a model of that definition of words with respect to each other, because it captures a lot of semantics. And actually, the attention mechanism lets you capture the semantics contextually, right? Which matters. It's not just defining the words, it's also if you have the semantics and then the semantics of the word in different situations, that's language. That's what we're building a model of. Also the pragmatics, how you use it in practice, what the colloquialisms are, how people tend to talk. It also captures a lot of patterns, and this is where we can get in trouble. And I don't want to talk too much about this because it's a bit of a rabbit hole. But it will pick up on fact patterns. If it sees a pattern enough in the wild, it will be able to reproduce it pretty reliably. But that's not the same thing as knowing a fact, as to be trained on a fact pattern. And it has reasoning patterns. If it sees like a certain way of thinking enough in its training data, it can reproduce those with some fair amount of accuracy, or even produce things by analogy or extensions of them. Does that count as true reasoning? Not in the way somebody writing an inference engine would think of it. And it's certainly not 100% reliable. For a programmer, what's the API? I want to use them. We have a model. We have all the measurements of language. How do I take measurements? How do I get things out of here? This is the entire API of language models. It's a pure function that predicts the next token. All I've done is emitted a bit of high school level algebra, and in those 3 dots there. But then I get the probabilities of the next token given a sequence of all the previous tokens. And that really works. And if I want to get many tokens, I just iterate over that and choose the most probable one at each step. Simple recursive function generating text. What I emitted is that it's a very true statement that I emitted some high school level algebra in there. It happens to be a trillion-ish floating point operations and about hundreds of billions of constants. So it really doesn't fit on the slide. But that's all a model is. It's a pure function. And it's a pure function that does math and has some constants in it. That's what training is finding the constants for the function. So how does it work? I give it a sequence. I say, Mary had a little. And because it's seeing patterns all over the internet, it says lamb. That is by far the most likely answer, because that's a very common little rhyme in the English language. And I say Mozart had a little. Well, it's not lamb. That doesn't make sense. It says sister. Why does it say sister? I don't know. Could have been anything. Bit, star. Those are less common than sister, but they're up there. Also, star is up there because Mozart wrote the music for Twinkle Twinkle Little Star, which is probably captured in the internet. It turns out that the reason sister is up there and brother is not is that Mozart does have a sister, and he did not have a brother. So you can see we're sort of capturing fact patterns from the training data, but also not in a 100% reliable way. It's just kind of all in the stats. Incidentally, the sister was older, so this is an incorrect fact. But just because he had a sister, that bumps up the probability of that word. So I want to add this to my toolbox. I have a bunch of tools. It's great that I can use this model to kind of academically understand language. I have a lot of tools at my disposal to do that. And I want to add this tool to my toolbox. But I'm still trying to figure out how to use it and how to get it to do what I want it to do and do something useful and beyond a chatbot. Chatbots are great. I think we've fully explored the capabilities of ChatGPT all on our own. Now we want to build more interesting things that maybe provide a little more societal value. Well, if I have a pure function and I want to get different output, what are my options? I can either find a different function, but I don't have millions of dollars to train a new function. So my options are, I can change the input. It's literally mathematically the only thing I can do to get different results or better results out of a language model. And this is the entire field of quote unquote AI programming, is putting the right stuff into the model to try to get it to get out the stuff that you want. Where does this data come from? You can have human input, like a chatbot or a programmer manually putting in input. You can have an old-fashioned program, like a regular program that builds a bunch of strings and concats stuff and then sends them off to the model. You can have the result of one model feed into another model, or the same model invoked recursively, and really any combination of the above. And all of AI programming, unless you're working on the models themselves, is some combination of these. Altering the inputs of the function in various ways and building programs to programmatically alter the inputs of the functions. There's a bunch of patterns for this. This is just descriptive. This is how people are using these out in the world. The simplest one is prompt engineering. If I have user input and maybe a history of past messages, how do I get the language model to act different or emit different things? Well, I give it a system prompt. I may say, talk like a pirate, or emit JSON, right? That's the system prompt. Prompt engineering is not engineering. It's just trying to find stuff and experimenting around with the model. This one's really gaining a lot of popularity, which is, you want to sometimes feed real information into the model that maybe it can't reliably get out of its internals. So you take the user input, you pass it to a search engine, could be a keyword-based search engine, semantic search, doesn't really matter, and you pass the top-end results, along with your system prompt and the user input, into the model, right? And assuming your search is good, assuming the data that you want to talk about or you want the model to relay to you is, assuming the data is there, the models do a good job. The attention mechanism is actually pretty reliable at kind of zeroing in on the relevant parts of the input data. Of course, if your search wasn't good, and you don't have good recall, and the answer you actually wanted is not in the top-end results, the model is back to bullshitting. And it will not be able to give you reliable information. Okay, so an extension of that is we're going to invoke the model twice. We're going to invoke the model, and we're going to give it our database schema and a question from the user. And we're going to say, write some SQL that answers this question. And this actually works for simple queries and simple databases. You get the results from the database, then you call the model again with all those results and the user input. And it works, but it's completely reliant on the ability of the model to generate SQL code and to do so correctly. And also, you can't code review it before it runs if you're using it in production. So some issues with this, but people are using it effectively. And if you can get your queries simple enough and your schema simple enough, you can get some reliability up there. Another big thing, OpenAI just released this feature a few weeks ago, is tool use. I can alter my inputs such that the model can emit JSON that matches a certain pattern, which then I can pass off to an API, which may go to the side effect in the world. It could order a pizza, and then it can go back and feed it into the model again. So, people talk about tool use as if the model is doing something incredible, but all it is telling the model to emit API calls, and then some external system has to observe those and actually execute them. And then the other big thing that is really highly hyped these days, and there's a billion startups and people are talking about this is going to lead to AGI and whatnot, is this concept of agents. All agents are is arbitrary combinations of the above patterns and invoking language models recursively. That's it. At the end of the day, each model invocation is still a pure function of input to output, and we're still just trying to marshal up the correct inputs at each phase. And this is actually, I think, closer, building a good agent, I think, is closer to traditional software engineering than it is to magic AI programming. It is different from traditional programming in one way. Did it work? The model output is always going to be a bit opaque. It is going to be deterministic, but it will be opaque. And it can be non-deterministic if you decide to turn up the randomness. It's not like regular programming where once a function works on a variety of test cases, you can be pretty sure it works. It needs to work across all test cases, and the only way to validate that is statistically. You have to apply experimental techniques to actually give it a variety of inputs and then see what your result success rate is, and do data-driven analysis of the results. And you need to know your problem domain. Like for some problem domains, 90% accuracy may be great. For other domains, you may need 5 nines of accuracy. Probably not going to get that from a language model ever, but you need to know what that number is. All right, so that's the state of language model programming today. All the furor and activity, and I can't keep up with all of it, but everything I have kept up with and have read falls into 2 categories. It's either improving the models themselves and like the core data science used to train them, or it's working on what are techniques for giving the models better inputs so that we can get better outputs, and what kind of programs can we write up as a scaffolding around the models to formulate those prompts. Mixed success. This is a very active field. Sometimes they work well, sometimes they don't. One thing I do well in programming, we all do well here, is data and logic. We've been working with data and logic for quite some time. Business logic, data, databases, we're all very comfortable with those. And we write programs that work between them a lot. We also have language now. We can now work with language using the techniques I just described. But it's still, how do I get my data to meet my language, right? I can just shove it in the prompt. I have to shove it in the prompt, the context, the input to the pure function. That's the only thing I can do. There is no other way I can make my data accessible to a system. And what's the best way to do that? What possible technology kind of lives in the intersection of data and logic and language that kind of has a foot in each world, such that I can work with it in a very data way on the data side and work with it in a very language way on the language side? And obviously, this is a leading question. It is RDF. So we should be putting RDF data in our prompts, and when we are asking to get kind of more structured data out of models, we should be asking for it in RDF format. And this works quite well. So at a syntactic level, well, let's step back and talk about Noam Chomsky. Always love to do that. Good old Noam. He's still kicking around. This book establishes the concept of a generative grammar, which is a language model. It is a simple language model that fits on a page. That math right there is his language model. It's a generative grammar of language and how it works. He built it based on observing many languages and trying to kind of figure out what is the essence of language, or this language, particular languages, or all languages. Chomsky believed that there was a biological basis. These rules are actually in human brains, that there was like some mutation that gave us these rules, and that's why humans are language-using creatures. And you know, this is different for every actual language, but one thing that is super foundational is subjects, predicates, and objects, or subjects, verbs, and objects. You know, there are languages that kind of stretch the definition in one way or another, or a little bit more confusing, but there's something pretty fundamental to cognition in this, and that's what Chomsky's exploring in this book. And so when we go back to a language model, because the language model is trained on language, those concepts are also sort of baked into the language model. They are captured, they are measured as part of the model-making process, the process of measuring. And so RDF is really surprisingly good at going back and forth between natural language and RDF. You can go to any snippet of text and paste it into ChatGPT and say, give the facts here in RDF format. And if you want it to do an even better job, you can say, give me the facts and here's the predicates I really care about. You know, given this list of predicates, find anything in here that could be relevant to those predicates and give it to me in RDF format. And the other way works well too. You can give it RDF data and then just have a conversation with that data really easily. And it works better, in my experience, than trying to upload CSVs or spreadsheets or any of the other ways you can get structured data into a model, because they're just statements. And the difference between a statement in language and a statement in RDF is not that big a conceptual leap. Tool use. It also does a good job of tool use. There are many things that currently people use tool use for. Say I have this question. Who are Luke's parents? And I want to ask it of the model, and I want it to use a variant of tool use, which is the query generation, right? Say I want to do this with RDF. The model can emit an RDF query. Luke is the child of who, right? It can convert that statement, that English statement, or that English question into this RDF question. And here's where RDF shines. So far, this is not that different than SQL, right? It's just a different query format. What if my RDF implementation supports reasoning? Now the language model is asking a different question. Who is Luke a descendant of? It's a different question I can ask. But the language model doesn't know any different. To the language model, this is exactly the same sort of question. We're querying about a property of Luke, even though under the hood, there's probably like a bunch of data log rules firing to answer this question and return the result set. But the key point is all that complexity is abstracted out of the model. And if you did something like that in SQL, you would have to like put all that in the model and make its tool uses much more complex. So RDF really simplifies tool use, at least as far as tool use involves calculating data. And you can even ask it like super complex questions that are much more open-ended over structured data. What is the relationship between Luke and Rembrandt? You know, that's a very open-ended question. Language model can't answer it. But if I have a full genealogical database and I have the correct inference rules in there, this query can precisely answer, you know, Luke is Rembrandt's 13 times removed great uncle, which is true. He is actually way back there in the family tree. But that's structured data. That is a true fact. That's not like maybe a fact pattern that it maybe saw somewhere on the internet. That's actually real logic and reasoning that gives me that answer. Let's talk about semantics. Well, we know language models model semantics. How do language models model semantics? Well, it's hard to get into it in our remaining time. But stated briefly, models have what's called a latent space, which is a high-dimensional vector space. Technically, it's a semantic field with a distance metric. But it's basically a mathematical, high-dimensional mathematical construct such that 2 points that are close in this mathematical space are also closely relinked somehow, conceptually. This is really abstract, though, this latent space of a model. These things are pretty opaque. There's a lot of research on how to observe them, how to interpret them. But you know, they're mostly opaque to humans. Even though they are a measurement of language, it's just a mathematical object with thousands and thousands of dimensions. The human brain doesn't easily wrap around it. Well, how does RDF model data? RDF models data as a graph, or concepts that are linked to other concepts. The human brain is pretty good at grasping data in this format. So, a knowledge graph, linked resources, I have a bunch of information. What you can do conceptually, and I'm still working on the best ways to do this in practice, is you can project your RDF conceptual map into the conceptual space. You can embed your concrete logical symbols and concepts into the conceptual space. And this does a few things. It gives you interpretability of that conceptual latent space. You can say, oh, this region of that space, that's where that fact landed. That tells me something about the topology of the space. I can kind of overlay them on top of each other. So it also gives me insights. I might say, hey, I had these two entities that I embedded in the model, and they landed pretty close. I'd never thought of them as close before. Maybe I should explore that relationship in kind of a soft way, right? So if you're trying to do exploratory information based on the data you have, that can be really interesting. The other thing you can do is soft inference, right? So what's one of the reasons the semantic web failed? Or indeed, why did attempts to solve AI with rule-based systems and logic alone fail? It's because the world is more full of rules than anyone ever has the patience to write down. There are so many aspects of the world, common knowledge, implicit assumptions, that it is impossible to enumerate them all as a human. And people try. Go look up the Psych project, COIC. They really tried. But it's hard. And even if I did it, my RDF graph would soon grow intractably large. But what the language model can do is it can kind of give me, for like really implicit things that are obvious, I can just ask the language model to give me RDF expressing the relationship between arbitrary objects, and it'll just spit out a set of facts that are most likely true, right? Because they're kind of implicit in the world, and they're implicit in what has been trained into the model. They may not be 100% accurate. Again, models are probabilistic. That's why I call this soft inference. But it means that we now have kind of like, we have the hard inference of our reasoning system, our inference engine, and we have the soft reason of the language model. And if you combine those together, you can do a lot of reasoning that you couldn't do with either one alone. And I think that's a pretty compelling. This is the central insight behind what's called neuro-symbolic AI. It's a small subfield of AI research. It's basically any research that is trying to combine the abstract fuzzy neural network with hard, concrete, logical symbols. And there's a bunch of different approaches for it. Some people are using Prolog to do this, kind of exactly the same way I described for RDF, but doing it with Prolog instead of RDF. Other people are like actually trying to encode symbols as items in this dimensional vector space, and then use that for training the models. There's a lot of complicated things people are doing. But if you're interested in this, this approach of using RDF to interact with language models is definitely it's a specific approach to neurosymbolic AI. So finally, the biggest problem I think with AI is a lot of people are using it for the wrong things. I don't want it to do my writing for me, or my singing for me, or my music playing for me. I don't even necessarily want it to do my coding for me. I find the code it produces kind of slop. But a lot of programming is dishes and laundry. It's the dishes and laundry of data, just like you were saying earlier. And particularly on the data side. So I think this is a tool to actually automate a lot of the dishes and the laundry of working with data. And I'm trying to build it. This is what I'm working on now, and if anyone is interested in talking about that, I'd love to chat with you. So yeah, we're going to bring back the semantic web with some AI under the hood. All right, thanks.